Welcome to this video lecture about other distributions. We've already looked at the binomial and Poisson distributions, which are discrete distributions that are useful for dealing with count data. We have also looked at the normal distribution, which is useful for dealing with measurement data that arises in a lot of situations. But some measurements do not follow a normal distribution, and so now we take a look at some of these other distributions. For example, the exponential distribution is a distribution that is a good fit for waiting times in between random events, that is, Poisson events. Because of this, it's a useful, simple model for failure times, provided that the failures occur at random. A more flexible model is the Weibull model, which can also be used for lifetimes, but can take account of burn-in and wear-out fail modes. Another distribution is the log-normal distribution, which is a positively skewed distribution that is useful for describing populations where the larger values can be very large, such as total bacteria counts. So how do we know what distribution to fit to a set of data? Well, we may know that the process operates in a particular way, that it satisfies certain assumptions, and therefore we would know in theory what distribution would be a good fit to the data. If we don't have such prior knowledge, we can take some data from the process and we can look at a histogram and see if it reminds us of some distribution. And then we can follow this up by using a probability plot. And we will now illustrate how a probability plot operates. Let's begin by looking at a normal distribution. This is the normal distribution probability density function. It has the familiar peak in the centre and the two tails on either side. If we represent this as a cumulative density function, this shows us, as we proceed from left to right, the cumulative number of values that are less than or equal to the current value. And so it has this sigmoidal shape. This is a probability plot when we transform the vertical axis so that this curve becomes linear. So a probability plot looks like this. It takes the distribution and it transforms the vertical axis onto a scale such that the plotted data will be linear if the data follows that particular distribution. So we can see here that the heights of Irishmen plotted on a normal probability plot falls approximately along a straight line, which indicates that the normal distribution is a good fit to those data. If we try a normal probability plot for the taxi waiting time data presented in Chapter 1, we see that it's not a good fit. It's very definitely not falling on a straight line. There's very strong curvature shown. But we could then try a different distribution, such as a log normal distribution, and we find that the plot is very good. So this suggests that a log normal distribution would be a useful distribution for describing those data. So this approach of using a probability plot allows us to check whether a set of data fits to a particular distribution. And we can use these plots, and then having identified the distribution, we can use that distribution to model the data and to make predictions about the future behaviour of that process. You can read more about this in the textbook in section 3E.